Snap.
Should I just start? Or?
Yeah.
Okay, cool. Hi, everyone. Thanks for coming. So today, just kind of a few words before the talk is that one, this is ongoing work, and I kind of finished the slides in 2 days. So it's kind of rough. So if you don't understand some part, it's not your fault, right? It's my fault. And two is that this talk may be a little bit bizarre in the sense of that it's a kind of interesting connection while I was digging into some question in the MDP system. And then I kind of find that there is a connection sort of to quantum system. And so today is a journey about that. Yeah, let's kind of have fun. So, okay, let's kind of start to kind of just state the question, like what's the question I'm studying here? I'm sort of studying like an old trick in the MDP system and also in OR, which is the following. So consider, let's say we have an agent system, and the states are S1 to Sn, right? And then there's a policy, map S1 to Sn to A1 to An. That's the action. And I'm interested in the following question. In what conditions the value decomposition holds? And the value decomposition is stating as, the value function on the whole state space from S1 to Sn as the sum of each individual component value function. Okay, and why you might be interested in this, why people might use this trick is more or less because of the dimension reduction, right? If you're looking at the left, the dimension of the value function is, S to the n is exponentially increasing. While you look at the right is, polynomial, right, in the state space. So the reason I kind of, start to kind of come across this trick is actually a conference in 2023. So I was in this business analytics conference while the Lyft team is presenting their great work on this. They won this Franz Edelman Award finalist. So they were trying to deploy RL in Lyft for their matching. And for the matching problem there, essentially you have a lot of drivers, and those drivers are agents in the system. And if you kind of view all the those drivers as a huge state, then applying kind of RL planning will be something like this, which is what they are trying to do. So you firstly try to learn a value function on the whole state. So S1 to n is driver 1 to driver n, and then you're trying to use learning the value function using something like temporal difference, which is a typical way of learning value function in RL, and then you can do something like policy iteration. And really the policy iteration here is that essentially each time when kind of a request comes in, you are going to pick up the driver with the largest value gain. And that's your policy update. Okay. But then turns out learning this value function is too hard because the dimension is too large. So they were using the following trick, right? Instead of learning the value function on the whole system, now they try to say I can learn the value function for each driver. And then more specifically, the feature here is a location. So learning the value function for each location, and then add it up to approximate the whole value function. And if you think about it, right, like does this make sense at all? Because the driver, they are not independent, right? Each step, if I assign this request to this driver, I'm not assigning to another driver. And if I have a lot of drivers, nearby, they may have some competition. But in any case, they use it. And so when I chat with them, the claim is actually this trick is very important. And they also don't really understand why exactly it kind of works, but it's kind of a natural trick to apply. Yes.
Why did you do this instead of doing the deep RL thing, where I just try to capture the arbitrary state vector using the deep and then trying to like?
I guess the reason is kind of similar. Is that it's too hard to learn that the function kind of over on like n variables. So you want to somehow decompose in a way that like easier to learn.
Okay. Like you're saying, I don't know. Like, do you know?
It's like interesting kind of regulator, right? You impose on your own kind of function, such that the function is easier to learn. That's my reading. Right. Okay, so then I kind of get interested in this question, like why they can do this. And then I kind of try to read more in the literature. The first thing I realized is that the similar kind of spirit, similar algorithm has been used also in DD, and also seems like it's working. And then kind of look more, I realized this is not a new trick. It's an older trick. Since kind of the 80s and 90s, when people start to think about the restless multi-arm bandit problem, and those also kind of a weakly coupled MDP problem, where they try to design the index policy. And if you think about the index policy, essentially you are trying to say, each kind of unit has their own value function, so that each step you can pick the guy with the largest index. And it's actually a decomposing condition applied to the value function. And that's actually essentially what the paper in 2008 from Alderman, it's a kind of a landmark paper in solving weakly coupled MDP problem. They are basically using this value decomposition assumption and then solving it with the LP and using the value learned as an index policy, as an index to kind of pick up the arm, okay? And then another kind of recent example is actually from Jackie and Vivek and Jonathan. They won the Peer Scholar Award, which is kind of applying this value decomposition idea to healthcare setting. And so the essence of all those papers is kind of this trick, right? I can decompose the value function by the sum of each individual component. But we don't really understand too much like why this works, in what system this condition holds. So this is kind of my motivation, like try to kind of dig in to understand this condition.
You actually need the value function to be decomposable. I understand that there's some literature that actually says that as long as when you decompose, optimizing for the separate components lead to the same decision as for the whole value function, then that's enough.
Great question. So then we should also understand in what system is weakly decomposable, right? So like there is some intuition, right? If the system is conceptually weakly coupled, then it should be fine. But what exactly that means? What exactly that means also for this decomposition? So that's exactly this talk about. So in this talk, it's basically my kind of journey diving into this problem, and then I realized there is a condition for kind of measuring basically how entangled a transition matrix is. And when I say entanglement here, is actually the similar entanglement used in quantum physics. And that actually directly connects to the value decomposition, decomposability.
I guess for the previous slides, so sometimes people do this decomposition in order to say this is an upper bound to the original value function. So all they want to do is to find an upper bound for the old optimal problem. But sometimes they actually want to derive a policy. But oftentimes, I think based on the decomposing problem, the policy is not feasible for the original problem. So then you need to do a bit more
feasibility mapping, yes?
Yeah, so one thing is you just want to find a bound to what is achievable in the original problem. The other is you actually want to find an action that works well. So you are thinking more about the former or the latter?
I think we will see kind of in a second what exactly it's about. I will say it's not, I have not even kind of explored too much in terms of optimizing the policy. Right now, it's kind of a given a policy, whether it's decomposable or not, or whether it's weakly, decomposable or not. Okay. Yes.
So try to understand just the setup of the problem, and so here you have one value function B, which is sort of lift
On the whole system, right?
lifts value function, right?
Is it-
Function for lift.
Yes.
Then VI would be the value function of one driver.
Yes.
They are saying the value function for lift is the sum of values for.
Yes.
So my question is, so I understand how the value of the lift is defined, but I cannot understand how the value of a single driver
add up.
can be defined, not even how that can be defined, because there is an equilibrium problem, right? So my value as a driver depends on what other drivers are doing. So like, I don't even understand like what's the definition of this. Like if you don't know the policies of other drivers, I cannot define individual drivers very much.
Yes. So basically, you are asking what's the reward here, right? So one reward is kind of let's say the revenue of this trip, right? And then in this case, then the driver get matched. They have that reward, and the other drivers get 0 for that request.
But my dynamics, I guess, also going to depend on what other drivers are doing. Like if another driver gets my trip, for instance, I don't get the reward. So to understand what is my
So that
dynamic,
essentially we're imposing a kind of an additivity for the reward structure here. Right, each step, each driver has a reward depending on their own action, which is matching or not.
Okay. So my value needs to include the forecast of what my competitors' drivers will do.
But in that case, you only depending on your own action, right? Your value depending on your action, which is matching or not. So it's somehow decomposing. Yes.
Nicolas' question is probably my value even at different locations depend on where is everybody else. Because there's
And
such
also what everybody else's policy is.
Right. Depends on where everybody else is. So the question becomes, when is the linear approximation okay?
Also, you're asking great question. We will actually get back. So I think the question is that the reward is additive, but is that value function actually well defined? Right? Because my value, if it's a long-term reward it doesn't only depend on my state. It actually depends on others. We will actually arrive there. Okay, good. So this talk is about kind of explain this condition, understand why in what scenarios it can be decomposed, and then start to kind of think about how to even quantify the kind of like how to quantify how much it can be decomposed. So it turns out that it will be something also close to the entanglement in the physical system. And then based on those quantification, eventually we actually can prove there is a general class of index policy in the multi-arm bandit problems. They are indeed weakly entangled, which is sort of answer the question that I kind of feel satisfied. They kind of explain the intuition why those systems you should apply this decomposability condition. And finally, just talk a little bit about whether we can propose better algorithms even beyond this value decomposition. Okay. And one comment here is that it's a kind of an interesting connection between MDP system and the quantum system. I hope this interesting work kind of opens the door. Maybe we can explore even more the connections, so that the techniques developed for one field might actually help another field. And also, this is ongoing work. Again, any feedback will be appreciated, and we might miss some reference, and so really appreciate any comments. Okay. So I think now we can kind of describe the problem formulation, like what exactly we are studying here. So for this talk, I will actually focus on the 2-agent scenario and the same results. It actually reviews the insight for an agent system. You will get something similar. By the way, this is also how actually quantum entanglement has been studied. People start from a 2-party and then generate to n-party, and the same path we are taking here. So let's say you have SA, SB for 2 state space, action A and B. Now, given your policy, you will actually have a transition matrix. And this global transition matrix is on the space, SA, SB times SA, SB. And you can write down the definition. So when your policy is fixed, then your transition matrix is fixed. Now, given this transition matrix, for the problem we are studying, we also assume there is an additive structure for rewards. So the reward for the whole system at this time step is a sum of the individual reward across all the agents. Yes.
How literally should we take, you got the action space as the product of the two action spaces, how literally should we take that? Because that's already suggesting that what one agent's actions can be is unaffected by what action the other agent.
That will actually be captured by the policy and the transition.
If you're not necessarily allowing, you may have restrictions, feasibility restrictions, that restrict you to a subset of that product.
Yes, exactly. But essentially, the transition kind of matrix controls that. Okay. And then this is the reward. Now we also consider the discounted version of this MDP, but the results actually also can hold for average reward. Okay.
You consider rewards as a reward per state. Does it matter, or is it also equivalent to consider reward per state and action?
Sorry, the what?
An alternate formulation is we can also reward for a state and action.
Oh, okay. Yes. Yeah. It can be also used for, actually the paper we are writing in a way depending on the action, but for the talk, let's say depending on the state. Okay. Just make the problem clean. Okay, so now after all the definition, now we can write down, what exactly the value function for the whole system is. Right? This is kind of the equation we are, I think, more or less familiar with in the RO, which is that V value function should equals to I minus gamma P inverse times this reward vector, right? Then this is a global value function. Now I need to define the local value function. And this is where actually things get a little bit tricky. Why? Because in the local system, it's not actually a Markovian system anymore. Right? In the sense of that, my state transition actually depending on other states. So to some extent, it's a partially observed MDP. However, actually in reality, people are running those LSTD or TD algorithm in any case in that subsystem. Right? Assuming those states actually are fully captured the structure. So if you are doing that, what that means? Right? If you're doing this, so it turns out you can actually define or sort of understand, capture what actually this will lead to for the local value function. So essentially, you can define the local transition matrix in average, right? If the whole system run into the stationary distribution, now in the stationary distribution, you can sort of average the long-term transition behavior into a local transition matrix, which is what I'm writing here. In the stationary distribution, in the condition I'm in the state SA, what is in average the probability I'm going to the SA prime in the next time step. And turns out if you are doing LSTD, just using the state, from the A system, your value function is this one. Right? Your value function is corresponding to this pseudo local transition matrix. And the question now is asking, whether in what cases VAB can be written down as a sum of VA plus VB. So this is the math structure of the problem.
So this B will change from the first definition to the second definition. The strategy in the first definition will be something that's optimal for the social planner, while the phi in the second definition is a strategy that's optimal for an individual agent under the new value.
Sorry, yeah. So here I'm not talking about the optimality. So I'm talking about a fixed policy pi. Right. You will have a global transition matrix. You will also can also define the local transition matrix. Okay.
Can you please say what is rho?
What is what?
Is rho?
Oh, sorry. Rho is the stationary distribution of the system. Okay, so now actually when I look at this problem, I realize it's hard to analyze because the structure here is like kind of here and there. Then I start to actually recall my kind of quantum 101 lecture in terms of a tensor product. because in the quantum world, people actually spend a lot of time studying the subsystem, global system, how they entangle with each other. And the most important tool they're using is this tensor product. And just want to quickly kind of check how many of you have kind of like heard of this or like use it kind of in the class? Okay. So since most of the people actually, and it's understandable, we are not familiar with this tensor product. So let me kind of walk you through a little bit. And it's not really hard. It's just something you kind of once you understand the definition, you will kind of start to understand how to use it. So the tensor product is defined as tensor product between two matrices. It can be generalized, but here let's focus on matrix. And so one matrix is A, which is N1 times M1. Another one is N2 times M2. And the A tensor B will give you a larger matrix, which is essentially each entry of A times the whole matrix B. And so you end up with a matrix with a dimension N1, N2 times M1, M2. Okay, and then each entry of A tensor B is actually a kind of a tuple. So for the entry ij from A and the entry kl from B, if you time them together, you will get the entry for n tensor B in the tuple, I comma k for the row and the j comma l for the column. So this is the definition. And this may actually feels like counterintuitive and you don't know how to deal with it. But if you think about the following question, let's say if we have two completely separable systems, and one system has the transition PA, another one has the transition PB, okay? And then I'm asking, what is the global transition matrix? How would you write it down? Is that question clear? Exactly. So because for the system PAB, it can be decomposed as PA times PB for each entry. So in the end of the day, this is what tensor product is, right? It tells you how to kind of compose different independent systems into a larger system. So it can be written as PA tensor PB. Now, kind of make the question a little bit harder. If it's a reward vector, the reward vector can be written as RA plus RB. In this case, how can we write it in terms of matrix and a tensor product? And this one is a little bit harder, but actually it can be written as RA tensor E, where E is all one vector, like all the entries are one, and the plus E times RB. And the reason of this, actually you can just read this like illustration, which if you have AB times 1, 1, you get AABB. And if you have a 1, 1 times CD, you get a CD, CD. And then if you add them up, that's exactly what you want for this equation. Kind of a cross, sum, right? Okay, so this is kind of a notation here, right? There's nothing really kind of new. But about tensor product, there are two kind of properties we want to use. One is this bilinearity, which is, if A plus B tensor C, it actually equals to A tensor C plus B tensor C. And another one is the compatibility, which is A tensor B times C tensor D, it equals AC tensor BD. Like all of those can be verified by just definition. And it's also kind of easy to intuitive, right? Okay. Now, after all those efforts, now we can go back to our problem and have a more succinct representation for the problem we are studying. So we actually are curious about the following problem, right? Given the transition, given RA, RB, we want to ask whether VAB can be written as the following, right? VA plus VB. And this is the same as asking, we can rewrite the VAB as this, the kind of use the transition and the reward to represent the value function. And in the end of the day, this is actually the equation we're asking. And now you may want to ask, why we want to kind of write such a complex form like this, because it actually enables us to start to actually, understand the system in a better way that I don't think we can do it without this notation. So let's start from actually an exercise. The exercise is the following. So because for the question I'm asking, I think there's obvious kind of a scenario that satisfies this decomposability, which is if A and B are completely separable. Right? They have nothing to do with each other. Then we obviously should have this hold. But that's the intuition. And how should you prove it? So I'm going to walk you through how to prove it under this new notation. Okay, it's actually an interesting process. So basically, the claim is that if PAB is PA tensor PB, can we prove this equation hold? So let's write this down. So let's say we focus on the RA tensor E part. And we want to show this part, R tensor E, will equals to this part. Okay? And to do so, we're starting from the left-hand side, and then by the I minus gamma P inverse, then by definition is actually also gamma K, gamma to the K times P to the K, right? And then we can kind of get the, so by definition, P pi is PA tensor PB. And we put the kind of the last, component out. And then we times PA tensor PB with RA tensor E. Okay? And by the compatibility, this equals to PA tensor RA and the PB times E, right? But remember, PB is a transition matrix, and the E is all one vector. So this will give you the E for any transition matrix. Right. So we get the same E here. Now we can repeat this process, and then we can get a PA to the K times RA tensor E. So now in this notation, everyone is tensor E. Then by the linearity, right, we can firstly sum over this guy and then tensor E. And that actually gives us essentially the VA tensor E. So I'm not using anything hard here, right? It's kind of all by definition. But it somehow makes the process rigorous now. And so far, it's still kind of nothing surprising. But the next question actually, I think, brings the problem to the next level, which is now if PA tensor PB works, what if it's a linear combination of PA tensor PB? Yes.
So physically, what does this mean?
Great question. So if all the xi are bigger than 0, then it's essentially your policy is kind of a random draw for a random variable. Right? And if the variable is I, each guy will act independently according to the TI. But if xi is smaller than 0, I'm not sure. So this is why, now kind of showing the power of the tensor product, because you may not necessarily have the intuition anymore.
With the sum of the VIs.
Weighted sum of VI. VI?
VAI and VBI.
The weighted sum?
Multiplied by X. Just guessing.
No, so actually the answer is that for this guy, it's still decomposable. Right, the VAB can still be written down as VA plus VB. There's no even weight. And yes,
What's the definition of PAI?
it's a transition matrix acting on the A system.
But sorry, what does the I refer to?
So I'm referring to if the PAB can be written as a linear combination of PA tensor PB.
Oh, so I can define them.
So I is arbitrary, yes. PAI is arbitrary, PBI is arbitrary.
Okay, but I thought PA was defined implicitly through the steady state distribution induced by the policies.
Okay, great question. So that is a PA pi.
Okay.
Right, that's the policy pi. So actually the first claim I'm going to say is about PA pi. So if PAB pi can be written in the following decomposition, so actually the PA pi can be nicely written as just sum over the weighted sum of PAI. And this is just a by definition. Also somehow makes sense if you're kind of thinking about like tracing out another system. By definition in the following sense. So this is the definition of PA pi, right? Now, because of this decomposition, PA pi can be written as sum over IXI PA times PB. Now, if you look at this sum, if you first take a sum on SB prime, which it doesn't really depend on anything, sum over SB prime will give you 1 here. Right? So this term is kind of cancel out. And then you take a sum on SB, which is only depending on this term, and will also cancel out, will give you 1. So what is remaining is essentially sum over XI PAI. Okay. But now what is really interesting is that for the value decomposition, whether it holds or not. Right. So it turns out that we can use exactly the same trick. You know, this is the kind of the left-hand side, and then we can expand by definition. And then by definition again, PAB pi is sum over XI. And then we put the last kind of, you know, like sum over XI, PAI, PBI, acting on RA tensor E. And again, every PBI tensor times E will become E. So it's sum over this guy tensor E. And then keep doing this, you get the same thing tensor E. And then this guy is essentially the VA. Okay.
I'm trying to ask you to help me form some motivation here. So if you fix the case where x is non-negative and sums to 1, then this is a mixture of independent Markov processes, right?
Yes.
And in that case, otherwise I had no idea. But
Yes.
in that case,
Why this is true?
would you expect that the value function is decomposable? This sort of means that it's decomposable conditioned on a random variable. That's obvious. Is there a good way to see that the mixing doesn't break that?
I actually like that. I was trying, but I didn't immediately get the answer. And then finally, I used algebra to kind of make it work.
Because if the transition matrix is a mixture of decomposable things, then that implies the stationary distribution is also a mixture of.
So that is actually not true. Yes, which is kind of interesting. And also, if you think about what does it mean for this kind of a linear combination of composable distribution, actually the linear combination of a composable distribution can give you anything because it's a vector. A separate vector, if you sum over a separate vector, will actually give you any vector. But I know there is in the queuing system, people like to think of the separable distribution, right? And I'm not sure whether there will be a connection here, but I think that's actually interesting.
Do you need any assumptions of the x here? Because otherwise, if x is like 0, say, then is not a valid transition matrix.
If X is 0?
Say all the xi's are 0.
Oh, yes, PAB pi is a valid transition matrix.
So, but then what does that mean on what X can be then?
Oh, good. Yes. So that's a good question. Not sure, but you can still kind of define this, right?
The math holds, but yeah.
Exactly. So if xi are all positive, sum over to 1, that is a transition matrix. But the negative, indeed, we're not sure. And actually, let me kind of just explain a little bit why I'm even thinking about a linear combination. It seems like out of nowhere. It's actually from my, like learning in quantum system. And in the quantum system, the sort of a 101 is to define what is a quantum entanglement. Because that's all the kind of, like all the kind of, what you are studying in quantum system is about entanglement. And the entanglement is defined in the following way, which is a kind of two-party quantum state, which is actually a matrix. And the dimension is exactly SASB times SASB. And if it can actually have the following decomposition, which is the sum over a linear combination of rho A tensor rho B, then we call it separable. Otherwise, we call it entangled. And the only condition for quantum state is that the quantum state has to be a positive semi-definite matrix with trace equal to 1. And that's the requirement for quantum entanglement. And so here, I'm trying to define something similar for MDP system. And this time, we focus on the transition matrix. And I call a transition matrix separable if it can be written as a linear combination of PA tensor PB. Otherwise, I call it entangled. And the only difference here now is that a transition matrix is, what is transition matrix, right? Coefficient is non-negative, and each row sum equals to 1. So that is actually a very different structure than a positive semi-definite matrix. So it will lead to a different kind of math, but I think the intuition here actually somehow we can borrow from each other. And what I just show you is that a separable, like why this is interesting, because a separable p pi actually will guarantee you have a decomposable value function. And what is actually more surprising is that another direction is also true. And this is actually the kind of surprising and sort of a non-trivial part. Now just want to make sure yes.
So if it is perfectly separable, we can see this argument. If we have a scenario where it's nearly separable, so separable plus some error term, can we also say that?
Great question. So later on, we're actually saying, if it's not complete, if it isn't perfect, if it had some, entanglement, that entanglement turns out will be a bound on the arrow of value decomposition.
We lost the reward function.
Yes.
How could that be?
Yes, sorry. So I kind of hide a little bit details here, but in another direction is actually, you have to hold for arbitrary reward function. I will make the another direction kind of a more explicit. But from separable to the decomposable, we just prove it. Right? That's for any reward function. Yes.
Intuitively, can we interpret like the xi as saying like there's a shared state of the world? And
yeah, so, okay, cool. So let's actually read this example. So just make sure we understand this, right? So let's say we have this two-agent MDP system, and each time your policy is that, with probability 1/2, you are going to take action A1 for one agent. Another one is taking A0, otherwise you swap. If this is your policy, there is a correlation. The correlation is that if I'm taking A1, you are taking A0. Vice versa. Similar to matching. So this system seems like they are correlated. However, from what we just learned, is actually separable. Because it's 1/2 P1 tensor P0 plus 1/2 P0 tensor P1. And there is actually a correspondence in the quantum system. People have studied basically is a correlation versus entanglement. And there are systems correlated but not entangled, which is actually also the case here. So also just want to have one comment on the sort of a coefficient. So I was thinking exactly the same question, is this, the coefficient do we have to make it negative? Like, can we just say we define a set as all the kind of non-negative coefficient? Because this set, P separable plus, is explainable, right? And physically implementable. Is this two set actually the same? But unfortunately, it's not, which might also make the problem even more interesting. So turns out we will actually be able to kind of even plot the polytype for the kind of different two sets. And then turns out there exists vertices that you have to have a negative coefficient to represent. And this is one example. So this weird transition matrix actually is separable, but you have to have a negative combination to get it out. So finally, kind of want to give you some ideas for how to prove another direction. Right. And the theorem we actually prove is the following. So let's say for a given PAB pi, and if for any reward vector, the value function is decomposable, then PAB is separable. So note that here we have to require for every reward function in the following sense. So if the reward are all 0, right, RA, RB are all 0, then obviously the value is decomposable because the value is also all 0. But that's not kind of interesting enough. We are really interested in kind of the essence of the system, which is actually the transition. So reward is not kind of the interesting part. Okay, so it turns out this proof is actually it's challenging. It's challenging, and also it's kind of interesting in the sense of that because we were studying this problem using the tensor product and using the kind of the space idea. So it turns out my proof has to kind of somehow correlate it with the geometry of the problem, of the space. So the first step I'm proving here is that if this I minus gamma P inverse, this guy is decomposable for every R, then I minus gamma P pi inverse itself is separable. Okay, so here I'm saying the separable is a linear space. Okay, so it turns out to prove this, I have to firstly sort of understand the P separable space, and then look at the orthogonal complement of this space, which is kind of a bizarre space. But somehow we can have a complete characterization of the space, like what exactly the basis is. And using that information, now if a matrix is not in the separable space, then we can find the orthogonal kind of projection. And using that projection, we'll be able to kind of construct a reward vector such that it's not decomposable. So I think this again kind of reveals the power of using the more complex algebra. It gives you something more. Now, one kind of a step is missing here, is that if I minus gamma P inverse is separable, and separable is a well-defined, right? It's can be written down as a linear combination of PA tensor PP. Then P is separable. So this is a simple statement, right? If I minus gamma P inverse is separable, then P is separable. And actually, it's easy to see another direction, right? If P is separable, then I minus gamma P inverse is a linear combination of, so if P is separable, actually P squared is also separable. right? P to the K is also separable by the definition. So linear combination of them is also separable. So another direction is kind of easy. But the opposite is actually not obvious. And another kind of thing here is that if P squared is separable, it doesn't mean P is separable. Because P squared, for example, can be identity matrix. If we have this, I to J, J to I kind of a pairwise construction. But the P itself can be very entangled. But somehow, interesting enough, this one holds. So I'm actually going to leave it as an exercise for our students here. Who first one can solve this problem, you will get a small gift from me. It's actually a very nice, simple one-line statement of the problem. Okay, so now kind of one comment I want to make here is that this quantum entanglement structure is kind of in the heart of quantum information science. And by studying this structure, we have seen many fruitful results from teleportation to quantum sensing simulation and to quantum computing today. Actually, after 100 years of study, right? Now we are kind of facing a new entangled structure, which is, I call it Markov entanglement. Whether we can get, like many interesting things from it, I'm not sure. I guess we have to wait and see. But at least one thing we find is that actually it's an equivalent condition to the decomposability of V, of value function. Okay. So given the time, I'm going to kind of quickly walk you through a few results, which is the question actually people have asked, which is, like not many systems are exactly separable. Now, can you kind of quantify how entangled your system is? And turns out this is exactly the same question has been studied a lot in quantum system. And usually you define the quantum entanglement as the following. So an entanglement of a state is defined as some distance between this state and the manifold of the separable state manifold. Okay. And the distance function there usually is like some relative entropy, trace instance, trace distance. And there's actually a field called the resource theory, studying kind of view entanglement as a resource, and how you are going to kind of maximize the utility of the resource. Now, in the Markov system, I'm going to kind of use the same intuition, define kind of the same entanglement of a transition matrix in the following sense. And I need to choose the distance function, right? And it turns out different ways of choosing the distance function will also give us different kind of results or geometry. So the first distance I was thinking, which is kind of the most obvious distance, which is this total variance distance, the kind of a one infinite norm. Right? And this is kind of a one typical way of measuring distance, like in the MDP system. And so under this distance of two transition matrix, turns out you can show that the entanglement, how much entanglement you have, will bound the arrow of your value decomposition. And sorry, I was using Q kind of value in the paper, so it's the same for V. So it actually quantify, right? The entanglement of the transition versus the arrow of your value decomposition, and also quantify how much you can represent your PA pi with also kind of a decomposition here. Okay. Now, what is interesting is that now I kind of dig into this distance. Like think about what else we can define for the distance. And so it turns out instead of define the total variation distance for the whole system, we can also define the distance for each agent.
Like I instead of E of B.
Yeah, so sorry, it's the same as E rho AB. It's the same as EPAB, sorry.
Okay.
But essentially, policy will define your transition. So that's also kind of an entanglement for your policy. So if you define the distance in terms of agent-wise, it's actually more refined distance. Because in a lot of systems, you might have a larger distance, across all the agents, but actually for each agent itself, that arrow, that kind of each agent itself, the entanglement is much smaller. So if you define the same thing, you actually have the same results for the new distance. But this time is kind of agent-wise. And then you can also think about how about weighted distance, in the sense of that if you require for every starting point the kind of the distance is small, is too strong, you can consider, let's say, for the stationary distribution. You weighted distance by the stationary distribution because like there are some states you have more probability to visit, others you don't really care. And it turns out you can get the same thing. Weighted this time also the arrow of Q is also measured by the weighted distance. Okay. Yes.
Gamma, the discount factor,
Yes.
is close to one.
It's called yes, it's close to 1. Right. So you might want to have a better bound here in terms of average reward distance. Yeah, I'm not sure whether this can be improved or not. Yeah.
Kind of basically everything that can happen in the future, kind of aggregated.
Right. So actually, when we kind of arrive here, there's something interesting, which is exactly using this distance definition, I can prove for results I'm kind of wanted to prove in the beginning, which is that, let's say we consider the restless multi-arm-bandit problem. It's a well-studied problem. The problem is the following: you have n arms. Each arm has a state. Each time you want to pick up alpha times n arms, and for the arms you pick, they have the transition defined by P1. If you don't pick them, they have the transition defined by P0. And because of P0, it's called a restless. Okay. And so index policy actually perform pretty well for this problem like this. And the index policy is basically choosing the arms by their index, a function of the state. Okay. So now turns out in this setting, applying the distance we just talked about can give you the results that for any index policy that is not non-degenerate and has a reasonable speed to converge, you can actually show for those policy the entanglement is small. It's 1 over root n. And the condition we are applying here are actually exactly the same condition used in the literature, which you have to somehow make sure the system is converged and non-degenerate to make the policy make sense. And the intuition here is that actually when n goes to infinity for the index policy, when n goes to infinity, with high probability, when you make decision, you can look at your own state. You don't have to care about other states anymore. That's kind of the separable kind of intuition. But it requires that exact distance kind of a measure. So I find this interesting. We also did some experiments. It's actually consistent with this square root of n intuition. Finally, just kind of 2 minutes, very quickly about what we are thinking. Kind of can we propose something beyond value decomposition? The same intuition also has been used in quantum physics, which is that not every state are decomposable. Can you kind of represent the state in a way that is not separable, but still efficient to compute? It doesn't require exponential time complexity. And actually, they have a lot of success in the physics world. Now, in the Markov world, we are not sure. So one function class I'm thinking is that instead of completely separable, learning a independent value function, maybe we can firstly compress the overall state to give you a low dimension representation, and then share this representation to every single state, and then they learn a value function and then add up. So if you're not sharing anything, then it's completely separable. It's separable. Now, let's say we share 1 bit, 2 bit. Will that be actually better to learn the value function? We are not sure. One thing I was actually ambitious enough is that after I have this algorithm, I was like, I saw a kind of a competition called the Robot Runners. And it's actually a serious competition, which is sponsored by Amazon Robotics. And you want to kind of do scheduling and routing for robots in the fulfillment center. So I was ambitious enough. It's like, let's try this competition, like using the fancy algorithm. So we actually team up with a friend from CMU with her group. The results actually not bad. We get rank 2 among 40 teams with a lot of hacks. But unfortunately, we did not make RL work. So not even mentioning our algorithm. Like the RL eventually the one we make it work is a greedy algorithm with a lot of hacks. So we are still kind of in the exploration. With that, I want to thank everyone. Any question, any feedback are welcome. Thanks.
That's how you gauge it. That's how you gauge it.
No, I am thinking like.
Okay, now that's actually the back. Where are the other messages?